the first thing that I want to do is introduce the concept of a probability distribution. And the best way to think of it is that a probability distribution represents a variable's idealized frequency distribution. So it shows all the possible values that the variable can take and the chances, or the probability, of each of those values occurring. And they are related to frequency distributions because, if you think about it, frequencies in a sample are based on the underlying probabilities of those values occurring. Now that's enlightening, but it's also a lot to take in. So let's look at an example. Imagine that you're rolling 2 dice and then you're adding them up. Well, if we look at the probability distribution for that population, it tells us 2 things. 1, all the possible values that we can obtain are expressed along the x-axis. So you can get any number from 2 to 12. Nothing more, nothing less, nothing in between. And 2, the probability of getting each of those results is expressed by the height of the bars, all of which add up to 1 or 100%. And we can confirm that if we overlay the bars with the different combinations of dice that make up each sum. So that's the probability distribution. Now let's say that we actually go out and roll 2 dice a bunch of times, or take a sample, and then plot the frequency distribution of that sample. Well, if we roll the 2 dice 50 times, we could get something like this, or like this, or like this. But what if we roll the dice 500 times instead? Well, then the frequency distribution would look more like this, or this, or this, which clearly looks a lot more like the probability distribution over on the left. And now imagine that we had a sample size of 50,000 instead. I think you're getting the point now, but let me lay it out either way. In an infinite sample, a variable's relative frequency distribution is equal to its probability distribution. That's why I refer to it as an idealized frequency distribution. And that's an amazing discovery because it means that if you can identify that your sample follows a known probability distribution, then you can use it as a model for the entire population. This example follows a binomial distribution, and it can be used to calculate the probabilities on the outcome of rolling 2 dice without actually needing to roll them 50,000 times. So that's what we'll be attempting to do in this section. Alright, so I keep mentioning all these known probability distributions, so it's about time I show them to you. Probability distributions can be broken down into 2 types, discrete and continuous. Now, under discrete, we have examples like the uniform distribution, in which the probability of each outcome is exactly the same, like rolling a single dice. We have the binomial distribution, which we saw in the previous lecture. And we also have the Poisson distribution, which gives the probability of an event happening X amount of times in a given time frame. In this case, we're showing the number of website visits in an hour. Now, discrete probability distributions like these have 2 distinct properties. 1, the height of each bar is its probability, and 2, there are gaps between the numbers. And that just means that you can't have any values in between. You can't have 2.5 website visits in 1 hour, or you can't roll a dice and get 3.7. Now we also have continuous probability distributions. There's a uniform distribution here as well. There's an exponential distribution, which expresses the amount of time between 2 events, like the minutes between customers arriving. And then there's the normal distribution with its famous bell shape. Now, contrary to discrete distributions, though, the height of the curve is not its probability here. The area under the curve is. And in these distributions, the numbers can take any value. You can have a baby weigh exactly 4 kilograms at birth, but they can also weigh 4.001 kilograms. So those are the types of probability distributions. We're going to focus on the normal distribution going forward because of all of its applications, but the same concepts can apply to the rest It's just the formulas that change a little bit.